Okay, sir, we are live now. So there was a disturbance morning.
और आवाज तो क्लियर है सर.
Everything is fine. Sneha, so अभी actually 10 minutes है sir, technically speaking. So will be join after 10 minutes.
हाँ ठीक है, वो अभी तो टाइम भी ऐसा है ना.
आज पूरा मुंबई में सब लोकल एंड एवरीवेयर देयर वाज एन इशू. सब न्यूज चैनल पे और सब आ रहा है. देयर वाज some स्ट्रीम कितना स्टेट इलेक्ट्रिसिटी यूज होता है टाइम. So
But
at times some
they
kind of trip
resolved
has happened.
such a big issue very quickly, no?
Never means we have never encountered such kind of thing in Mumbai. A sudden power shutdown. कभी नहीं होता. Rarest of rare. Yes. ऐसे कभी भी हो सकता है वरना जिंदगी में.
सर माझी स्क्रीन विजिबल है ना?
Yeah, it's visible, madam. You can actually keep search this on.
अच्छा, should I keep that? Okay.
Okay. Next. Naushad sir, shall we keep
Yes.
tomorrow thing 5 to 7?
Tomorrow 5 to 7 for lab session.
Ask participants. See, tomorrow morning they have 10 o'clock to obviously Damodar he will be taking. So they will, since it's a cadence tool, they will go on having the theory and the demo both parallelly. But I think in morning majorly they will be talking about theoretical aspect. And then at 2 o'clock, then
Will it
they
be
will
possible to
yes.
hold the lab session on Wednesday evening?
Yes. Tuesday or Wednesday, any one day.
So if it is possible for you, so please schedule on Wednesday evening. If it is possible, and if there is any issue, I will try to manage tomorrow.
No, we will ask the participants. We will ask them also their opinion. What is their feeling?
Okay.
So I'll ask. I have created a kind of a poll question for them. They can reply on that. What is their choice afterwards?
Okay, it's okay. No issue.
In meantime, what I will do, I will show one video. Our department, electronics department. Back as a presenter. Small thing is there. Show that.
Sir, should I share the screen?
Yeah, please.
Yeah.
Okay, I think we should start the session now.
Sir, is it visible?
Yeah. Naushad sir, shall we start?
Yes, I'm ready. No issue.
Oh, okay. Then I'll start. So welcome everyone. Welcome back for this next session. Sorry for the interruption. There was a major power failure in Mumbai, and that's why we had to shut down the session, which was supposed to be there at 11:30 by Dr. Naushad Alam. Now the same session will be taking right now, and the contents which we are supposed to cover in these 2 hours, we'll have to reschedule it either tomorrow evening or day after tomorrow evening. So I will ask you that poll question afterwards when everyone joins to the meeting. Let us say after 1.5 hours or maybe at the end of the session, we can decide collectively when we should reschedule the session. Okay. But right now, this particular session is about high-speed CMOS logic design, and the speaker for this session is Dr. Naushad Alam. And it's my proud privilege to introduce to Sir. Welcome, Sir, to S.P.I.T.
Thank you, Professor.
Dr. Naushad Alam received his BTech degree in Electronics and Communication Engineering from Jamia Millia Islamia, New Delhi in 2003, and MTech degree in Electronic Circuits and Systems Design from Aligarh Muslim University, Aligarh in 2009. He earned PhD degree in Microelectronics from Indian Institute of Technology, Roorkee in 2013. His doctoral work was on nanoscale circuit design, considering the impact of process-induced mechanical stress. He has published 25 papers in SCI index journals that include 10 IEEE transactions and 33 papers in reputed conferences such as ISQED, IEEE ISCAS, IEEE TENCON, IWPHD, VDAT, IEEE ISCD, and IEEE UPCON. He has received 4 Best Paper Awards at ICSCI 2008, Impact 2013, VDAT 2015, and Impact 2013 respectively, and delivered various keynote talks, including Big Misra, MNIT Jaipur, and he had earlier delivered a session at S.P.I.T. also in 2015, which was well received by the audience. And he has supervised one PhD thesis on robust SRAM design and presently supervising 3 PhD students. He has also successfully executed a UGC-funded research project on TFET-based SRAM cell design for IoT applications. His research interests include device circuit co-design, robust nanoscale circuit design, low-power circuit design, PVT-tolerant circuit design, near-threshold, sub-threshold circuit design, etc. So as far as I know, Naushad sir, this is his technical profile. But if I would like to introduce Naushad sir in a different manner, he's a very humble person and always ready to help. Always anybody can approach him and he will never say no. And he will try his level best to explain each and every concept. So welcome, Naushad sir. I am very happy that you accepted the invitation. And not only this theoretical session, but you will also be taking our few laboratory sessions, like hands-on session on LT-SPICE, and then electric design systems. So I was very happy when Naushad sir accepted and he said that, okay, we have other options also available, so that if people don't have right now cadence with them, I will give them the training. I will tell them how to do the circuit simulation, how to do the layout simulation, how to do the layout versus circuit simulation. So it is up to you, participants, how much benefit you can extract from our renowned speaker today. So I hand over this session to Naushad sir. So Naushad sir, platform is yours. You can
Thank you,
go ahead.
Professor Raghav,
I'll
for
share the
the kind
screen.
words. I request you to please enable the screen share for me.
Yes.
So welcome participants to this session. This session on high-speed CMOS logic design. So in high-speed CMOS logic design, we are going to learn about a methodology that is referred to as the method of logical effort And method of logical effort actually helps us in three ways. It helps us in estimating the delay of a given logic circuit. Subsequently, it helps us in sizing the transistors of the logic gates in a given logic network for minimum delay. And it also helps us in sizing the logic path for minimizing the delay of a given logic network. So transistor sizing and path sizing, they are two different concepts, and both of them are employed for minimizing the delay of a given logic circuit. So that will be the focus of today's talk. So I have arranged this presentation in this manner that first we shall have an overview of MOSFET capacitances. What are the various capacitances appearing in a MOSFET? And then we will see how we estimate the delay of a logic gate, and we will take the case example of an inverter, where we will see how we can derive the expression of a logic gate, and subsequently that delay expression of logic gate will be transformed to the method of logical effort. So as I told you, that method of logical effort helps us in estimating the delay of a logic gate or of a logic network. It helps us in transistor sizing for minimum delay, because we often come across a situation where we need to size transistors. So we shall have some methodology, some technique, some for estimating the capacitance. So total capacitance that you see is the capacitance of this and this. So total width that you see is the width of P MOSFET and width of N MOSFET. So you have WN plus WP. So now you can see that we have represented the input capacitance of this inverter in a very, very simple term. That is, you have some constant term here multiplied by the total width of the transistors connected to a particular input. Right? Now come to the calculation of parasitic capacitance appearing at the output of the inverter. So this parasitic capacitance is also referred to as self-capacitance. So now here we have this inverter with all the capacitances appended over here. So here CGSP, that actually includes all those terms, means the overlapped components and the gate capacitance component appearing between these terminals. Now here you can see that we have to estimate the capacitance at the output node. So this term and this term, they do not appear at the output node. So they go away. They go away because they are not connected to the output node. So that is why you are not seeing here. Now these two capacitances also. So you can see that P MOSFET, the body of P MOSFET and the source of P MOSFET, both of them are connected to VDD. So you can see that this capacitance actually is shorted. The two terminals, they are connected at the same potential, so this also goes away. Similarly, the two terminals, they are shorted, so this also goes away. So you are left with these capacitances that actually contribute towards and to the output node, right? So from here, we can actually write the self-capacitance of the inverter, like C self can be written as the CDBN, that is drain to body capacitance of N MOSFET plus drain to body capacitance of P MOSFET, plus 2 COL because of N MOSFET and 2 COL because of P MOSFET. This 2 again appears because of that Miller multiplication. Now we can write CDBN as the technology constant junction capacitance per unit weight, junction capacitance per unit weight, and then COL, and therefore the self capacitance can actually be represented as the product of the C effective and the total width of the transistor. So C effective actually represents the total parasitic capacitance per unit weight, and this WN plus WP is actually the total width of the transistor. Now come to very quickly, let's go ahead with the delay calculation of an inverter. So we will consider first case 1 when the input is switching from 0 to 1. So you can see that when it is switching from 0 to 1, this is off, and when it was 0, so C out was charged to VDD. So when it has turned on, now it is offering some on resistance, which is referred to as Rn. So you have an RC network through which this capacitor is discharging. So we can use the response of RC network, V out is equal to VDD multiplied by exponential minus T upon R on C out. So this we are familiar with this expression. This is the this we have learned in the response of RC network. Now, since the delay we have defined as 50% point, so we will actually calculate the time required to discharge this CL from VDD to VDD by 2. So for solving for V out is equal to 0.5 VDD, we get this expression 0.69 R on multiplied by C out, where C out is the total capacitance seen at the output. Because in addition to the parasitic capacitance of this inverter, you may have connected some other gates at the output of this inverter. So those gates will actually contribute to the C load. So this C load appears because of the gates connected to the output of this inverter, and C self is appearing because of the self capacitance or parasitic capacitance of this inverter. Similarly, when the input switches from 1 to 0, so now when it was 1, so initially the capacitor is discharged, and when this has switched to 0, so PMOS turns on and this offers a on resistance of Rp. So now again you have an RC network, and this capacitor is actually charged through this resistor. So again we can use the response of RC network expression, and we can arrive at this delay expression. Fine. Now we can represent the average propagation delay. So average propagation delay is average of the two propagation delays that we just calculated, and we can express the average propagation delay like this. So this delay expression we derived using the RC approximation of the inverter circuit. We can also derive delay expression using the charging and discharging current, which is referred to as IHL. So IHL is actually the current which is responsible for charging the for discharging the capacitor through N MOSFET, and ILH is the current that is responsible for charging the capacitor from 0 to 1. So again we will consider one case when the input switches from 0 to 1. So when the input switches from 0 to 1, so when the at t is equal to 0, when the input was 0, so the total charge on the capacitor will be C out VDD. Now at t is equal to TPHL, that is 50% point, the capacitor would have discharged to VDD by 2, and therefore the charge left on the capacitor will be C out multiplied by 0.5 VDD. So the total charge that is drained from the capacitor is 0.5 VDD C out, or I can say that this is the total charge that we need to drain out from the capacitor. Now this is the total charge to be drained, and rate of flow of charge is given by the discharging current IHL. Therefore, time required to drain this charge is given by the amount of charge that we want to drain divided by the rate of flow of charge IHL. And when we put this thing here, so we get this delay expression in terms of the current. So here we are getting this delay expression. We have derived this delay expression in terms of the discharging current. Following similar procedure, we can derive the expression of delay using the charging current. So you have similar expression, you can see. And now come to the symmetric inverter. So most of the time when you will be designing a logic gate, you would like the pull-up and pull-down network, the strength of the pull-up and pull-down network to be equal. Most of the time, not always. At times, in certain situations, we do design skewed logic gates, but most of the time, our focus is to design symmetric logic gates. And when we say symmetric logic gates, we actually try to equalize the pull-up strength and pull-down strength of that logic gate. So that pull-up strength, pull-down strength is equalized by making the pull-up current and pull-down current same. And that actually is achieved by sizing the transistor. So let's say if Wn is fixed, so you can size Wp. Now here we are considering a case when the Wp is made twice of that Wn. You know that this has been done with an assumption that the mobility of hole is half of the mobility of electron. Therefore, we must size the P MOSFET 2 times as the size of N MOSFET to compensate for the smaller mobility of holes and have equal pull up and pull down current. So if you have designed a symmetric inverter, ILH and IHL, they will be equal, and we can refer that as I out, or we can also say that the R on and R on P, they will be equal, and we can simply refer to them as the on resistance. So here we summarize the delay expression derived through for both the approaches. That is, here we are writing delay expression in terms of R on, and here we are writing delay expression in terms of I out. Now, when we write delay expression, here we have separated CL and C self. We earlier saw that the total output capacitance, we are derived these expressions in terms of C out, and we saw that this total output capacitance is actually the self. Yes, self capacitance and load capacitance. So CL there is actually a load capacitance. You have a load capacitance, you have a self capacitance. Now here I am making some manipulations. So what I am doing, I am writing C out as CL plus C self. Now this CL plus C self, what I am doing, I am introducing this C in term here, and then we are having this C in the numerator here, C in the denominator here, So we can write this thing as this. Similarly, this thing actually can be written as this along with this. Now the purpose of doing this manipulation is, now for our inverter, this R on C in actually becomes independent of the size of the inverter. Similarly, the C in VDD upon 2I out, this term becomes independent of the size of the inverter. How? See, when you change or scale up or scale down the inverter, C in will proportionally increase and R on will proportionally decrease, and that actually scaling up of C in will be cancelled out by the scaling down of R on. Similarly here, if you increase the sizes of the transistors in an inverter, C in will be increased and I out will also increase by the same factor. So a scaling factor will again be cancelled here, and therefore you can say that this term here and this term here now becomes independent of the size of the inverter. So this thing and this thing now becomes a technology constant for an inverter, right? So that thing actually has been written as tau here. That thing actually has been written as tau here. So tau actually is a process parameter, now becomes process parameter, which is constant for a given technology, right? And then you can see this term here, they are similar. So the coefficient of this term here is 1 and the coefficient of this term here is 1. Okay. So we can actually write this delay expression in this way: P tau multiplied by GH plus P, where this ratio actually has been written as H, and in the method of logical effort, this is referred to as electrical effort or fan out. And this term actually has been replaced by this P, which is referred to as parasitic delay in the method of logical effort. So we can actually write this thing, this delay expression like this, where this tau becomes process constant And here in this particular expression, G, the value of G is actually 1. Here in this particular expression, G is 1 because this is the delay expression for inverter, and in the method of logical effort, the inverter is assigned a logical effort of 1. So now let us see the method of logical effort. So in the method of logical effort, delay of a logic gate is expressed like as tau, which is a process parameter and has the unit of time. So this tau has the unit of time, and what you see in the bracket here is actually a unitless quantity. You can see over here, this is a ratio of CL upon Cin, this is a ratio of C self upon Cin. So this thing is actually unitless quantity. So when I said that this is parasitic delay, so this parasitic delay actually is a unitless delay. Okay, so the unit of time is associated with this parameter tau. H is also a unitless quantity which is referred to as electrical effort. So this component in the bracket is a unitless quantity, or you can say that it's a unitless delay. And when you multiply this unitless delay with this technology constant tau, that gives you the absolute propagation delay. Okay, so that is what is summarized over here. So it's a process technology dependent constant, and G is referred to as logical effort. For inverter, logical effort is 1. In the method of logical effort, inverter is assigned a logical effort of 1. H is electrical effort, that is given by the ratio of load capacitance upon input capacitance. You shall be very clear about this. It is not the output capacitance, it is the load capacitance. So load capacitance is because of the external gates that you have connected at the output of the driver gate, and it is not the total output capacitance. Total output capacitance involves the self capacitance and load capacitance both, but we have already separated the self capacitance here. You can see that. So that shall be you shall be very clear about that load capacitance. And then the parasitic delay is given by the ratio of C self upon C in. So let us very quickly let us skip these things. Let us come to the delay of a logic gate, how we express the delay of logic gate in a method of logical effort. So the method of logical effort actually isolate the effect of fabrication process technology. This is important. This is important. So because if we have a logic network, given logic network, and we have actually the delay of that logic network calculated, so with the change of process technology, the tau will change and we will be able to estimate the delay of that logic network in a new technology. So that is made possible by isolating this tau with this D. And it expresses all delays in terms of the basic delay unit tau, that is process parameter. Okay, and absolute gate delay is actually given by the technology constant tau, which has the unit of time multiplied by the gate delay D, which is a unitless quantity. So, okay, so now come to the delay of logic gate. So delay incurred by a logic gate is actually comprised of two components. One is the fixed part, that is called the parasitic delay. Okay, any logic gate will have two components of the delay. One is the fixed part of that delay, which is called parasitic delay, and because of the self capacitance of the gate, and another is the effort delay or stage effort, which is because of the load that you have connected at the output. Okay, and therefore the unitless delay is actually expressed as the sum of the effort delay, which is referred to as, which is represented by F here. So this F actually represents the effort delay, and this P actually indicates the parasitic delay. So the delay of a logic gate is given by the sum of the effort delay and parasitic delay. Now, effort delay of a logic gate can be further expressed as the product of the logical effort of the gate and the electrical effort of that gate. So logical effort actually captures the property of the gate, whether it's a 2-input NAND gate, 3-input NAND gate, or it's a 2-input NOR gate or 3-input NOR gate. So that property will be captured by the logical effort of the gate, and electrical effort actually captures the load that you have, effect of the load that you have connected at the output. Okay, so this electrical effort is also referred to as fan out, and therefore this effort delay F can be written as the product of the logical effort of the gate and the electrical effort of that gate. So logical effort of the gate will remain fixed. For example, if we are talking about two input NAND gate, so logical effort of two input NAND gate will remain fixed irrespective of what load you have connected at the output. On the other hand, this electrical effort will actually capture the loading effect, the load that you have connected at the output of that two input NAND gate. So now putting it all together, we can express this gate delay as tau into D, and D can be expressed as that stage effort delay plus the parasitic delay. Now effort delay is actually given by the product of logical effort and electrical effort. Therefore, the delay of a logic gate is given by GH plus P. Okay, and tau you cannot see, so this is a unitless quantity here. When you multiply it by tau, that gives you the absolute delay in the units of time. Now comes the definition of logical effort. So how do we estimate the logical effort of logic gates? So logical effort of a logic gate is defined as the number of times worse a logic gate is at delivering the output current than it would be an inverter with identical input capacitance. Okay, that is, if the input capacitance of a given gate is same as the input capacitance of the reference inverter, then the logical effort of a logic gate can be given as the ratio of the output current of inverter to the output current of that gate. So you can see that if you make the input capacitance same, so what will happen? The size of the transistors in the logic gate will have to be reduced, and therefore the output current of the gate will also reduce, and therefore the logical effort, this numerator will be larger, and you will have some logical effort which is greater than 1. Other definition of logical effort is that it is given as the ratio of its input capacitance to that of the input capacitance of an inverter that delivers equal output current. So actually you have two situations. In the first case, you are making the input capacitance identical, that is input capacitance of the gate identical to the input capacitance of reference inverter, and then you are taking the ratio of the current of inverter to the current of gate. So that gives you the logical effort of the gate. On the other hand, logical effort of a gate can also be estimated by equalizing the output current. So you size the transistors of the logic gate such that the output current of the logic gate is equal to the output current of the inverter, and then you take the ratio of the input capacitance of the gate to the input capacitance of the inverter, and that gives you the logical effort of that logic gate. So this is the definition of logical effort of logic gate that we will be using, and we will be particularly using the second definition of the logic gate for deriving the logical effort of logic gates. So let us see how we can derive the logical effort of, say, two input NAND gate. So with that definition of logical effort, so this is the reference inverter. In the method of logical effort, we will always have a reference inverter. And with that reference only, we will be deriving the logical effort of other logic gates. So this is the symmetric reference inverter for which Cin is given by this. We have already seen these derivations. C self is given by this, and I out is equal. Now, from the knowledge of, for example, you see, if we are designing a two-input NAND gate, so in the NAND gate, the PMOS transistors are in parallel. So the pull-up network of the NAND gate, you have only one transistor sitting between the output node and VDD, either through this path or through this path. And in inverter also, you have only one transistor sitting between output node and VDD. Therefore, pull-up strength is same, and you need not to scale the size of PMOS transistor. So the size of PMOS transistor in NAND gate will be same as the size of PMOS transistor in the reference inverter. However, you need to connect two NMOS transistors in series for the two input NAND gate. So now two NMOS transistors connected in series will actually offer 2 times the on resistance as compared to the on resistance offered by this NMOS here. Therefore, to make the output current equal, you must have the on resistance of pull down network here same as the on resistance of pull down network here. So to achieve that, towards that pursuit, you need to double the size of these NMOS transistors, and when you double the size of these NMOS transistors, you will have equal the pull down current equal to the pull down current here. So you have actually, by sizing transistors like this, you have actually made the output current of two input NAND gate same as the output current of the reference inverter. Now from the definition of the logical effort, now once you have made the output currents equal, the logical effort of NAND gate can be given by the ratio of the input capacitance to the output capacitance. So we can actually prove that here. So what we can do, we saw the delay of the inverter. So similarly, we can see the delay of two input NAND gate. So we can write the delay of two input NAND gate as VDD C in NAND 2. Actually, it will be VDD by 2I out multiplied by CL plus C self. But I have introduced this C in the NAND 2 here in the numerator and then in the denominator here. So you can write the delay expression of the two input NAND gate like this. Now the delay expression of two input NAND gate can further written by introducing the input capacitance of the inverter. So we are introducing the input capacitance of inverter in the numerator here. Why we are introducing it? Because we are actually trying to estimate the delay of this NAND gate with reference to the reference inverter. So in the method of logical effort, we always have a CMOS inverter as a reference. So we have introduced this C input capacitance of the inverter in the numerator here, and therefore we have introduced the input capacitance of the inverter in the denominator here, So actually this thing can be written like this. Now once you have written it like this, you remember that this thing is nothing but, this is actually tau, the technology parameter. Fine. And this thing is nothing but the electrical effort, that is load capacitance upon the input capacitance. So this thing is H. This thing is nothing but C self NAND upon C inverter NAND. So this thing is actually the parasitic delay of NAND. Okay. And now you can see that this is the input capacitance of NAND, two input NAND gate, divided by the input capacitance of the inverter, and we just saw that this is nothing but the logical effort of the NAND gate. So you have the NAND gate. So you can see that we can actually write the delay of the NAND gate in terms of the logical effort, electrical effort, and parasitic delay of the NAND gate. Now we can actually, once we have got this expression that the logical effort of NAND gate is given by the ratio of the input capacitance of NAND gate to the input capacitance of the inverter, we can actually quantify the delay. So you see in the NAND gate, the width of the P MOSFET is 2WN and the width of the N MOSFET is 2WN. So total width of the transistor is 4WN, and we have seen the capacitance calculation. So total input capacitance seen at the input of NAND gate is this thing, and total input capacitance seen at the input of the inverter is this thing. So you can see these things get cancelled and you get the logical effort of NAND gate 4/3. Similarly, you can actually calculate the parasitic delay of NAND gate by putting, you can write the self-capacitance of NAND gate upon input capacitance of inverter as the self-capacitance of NAND gate upon self-capacitance of inverter multiplied by self-capacitance of inverter divided by input capacitance of inverter. Now, if you remember, this is nothing but the parasitic delay of inverter. Okay. And self-capacitance of NAND 2 upon self-capacitance of inverter. So this is So now this thing can actually be written as the effective. C effective is the total output capacitance per unit width or self capacitance per unit width multiplied by the total width of the transistor connected to the output node of NAND gate. So it is 2WP plus 2WN, and this is for inverter. So from here you can see that these things get cancelled and you get this NAND parasitic delay of 2 input NAND gate that is equal to 2 times the parasitic delay of inverter. Similarly, you can do it for NOR gate also. Since we are running out of time, so I will skip it and I will be providing slides. So anybody interested, he or she can see the derivations. So similarly, we can see the delay for 2 input NOR gates. And again, the delay of 2 input NOR gate, logical effort of 2 input NOR gate is 5 by 3, and parasitic delay of 2 input NOR gate is given by twice of the parasitic delay of inverter. So if we summarize, you shall actually verify that if the ratio of WP and WN in the reference inverter is 2, then for an n input AND gate, the logical effort is given by n plus 2 by 3. You can actually prove this. And the logical effort of n input NOR gate is given by 2n plus 1 by 3. Right? Similarly, you can also prove that the parasitic delay of n input NAND gate is given by n times P inverter, and n input parasitic delay of n input NOR gate is given by n times parasitic delay of the inverter. So you can prove that, and you may try to do that. So now comes a situation where we try to generalize actually that it is not true. Rather, because it's actually technology dependent. It is not that you will always need to size the width of PMOS twice the size of the width of NMOS. It is actually technology dependent. So here I am taking the ratio as gamma. So when you take the ratio as gamma, so you will here it is not affected because PMOS needs not to be sized, but NMOS will be made double. And these derivations are on the similar pattern, and from here we derive the expression for the logical effort in terms of gamma for 2 input NAND gate and parasitic delay of 2 input NAND gate. Similarly for NOR gate, so NOR gate you have PMOS transistors in series. So here, okay, I made a mistake here. I shall actually, oh right, it's okay. So 2 times WP, and WP is gamma times WN. So here you have, so again we follow the similar procedure and we derive, or I shall say we calculate the logical effort of 2 input NOR gate and we get it in terms of the gamma. So similarly you can do it for n input NAND gate and n input NOR gate also. So for an n input NAND gate, you know that n PMOS transistors will be connected in parallel and NMOS transistors will be connected in series. So by this knowledge, you can actually calculate the input capacitance seen at any input. So A1 here, sorry, this will also be A1. So A1 here and A1 here will be connected together, A2 here and this will be connected together. Okay, I should make this correction. To keep the diagram simple, I have not connected it. So it is actually connected like this. So you have a connection like this. So similarly, you have connection like this, and similarly, you have connection like this. So we actually, when we calculate input capacitance, so we calculate capacitance seen at any of these inputs. So for an n input NAND gate, you have n inputs. So we will be calculating capacitance seen at any input. So that you can calculate by using the derivations that we have seen, and from there you can actually derive the logical effort expression and parasitic delay expression for n input NAND gate and n input NOR gate. So that you can do that. That is what I have done here. So that will be done. So okay, let us skip this example. Now comes the multi-stage logic network. So till now, we have analyzed, like we have calculated the logical effort of a given logic gate. That is, we have considered only 2 logic gates, NAND gate and NOR gate. Okay, and parasitic delay of a given logic gate, that is NAND gate and NOR gate. Now, in a logic circuit, you will not have only one logic gate, rather you will have multiple logic gates connected in a chain. That is what we see over here. So you actually have a chain of logic gates, and that is referred to as multi-stage logic network, right? So for multi-stage logic network, we again define certain terminologies that we shall remember. So for path logic, for a logic, and this dotted line that actually represents a logic path. So for a given logic path, like we define logical effort for a given logic gate, for a given logic path, we define path logical effort. And path logical effort is actually given by the product of the logical effort of the logic gates falling on those paths, on that path. For example, on this path, you have this inverter, you have this NOR gate, this NAND gate, this inverter. So these are the logic gates that are falling on this path. Therefore, the path logical effort of this logic network will be given by the product of the logical effort of this gate, logical effort of this gate, logical effort of this gate, logical effort of this gate. Similarly, we have for a multi-stage logic network, we have another terminology, which is path electrical effort. So path electrical effort is given by the capacitance connected at the output, ratio of the capacitance connected at the output of the logic network to the capacitance seen at the input of the logic network. That will be given as path electrical effort. Okay. For a single logic gate, we had electrical effort, and for a multi-stage logic network, we have a path logical effort. And then we have another parameter which is called as path effort. So path effort is actually given by the product of the stage effort or effort delay of the logic gates falling on that path. So Fi is nothing but GIHI, and GIHI is nothing but the stage effort, okay, or effort delay of that stage. So GIHI, G1H1 into G2H2 into G3H3 into G4H4. And that is given by the product of the path logical effort and path electrical effort. Again, you can actually prove that the path effort, which is given by the product of the stage effort of individual gates falling on that path, can actually be given as the product of the path logical effort and path electrical effort. So these are the parameters, logical effort parameters, method of logical effort parameters for analyzing multi-stage logic network. Now, when we are talking about multi-stage logic network, there will be branching efforts also. Means you may have branching in the logic network. So when you have a branching in the logic network, so this again we define a parameter for that which is referred to as branching effort, right? So when you have a branching in the logic network, we have another parameter which is referred to as branching effort. So for example, you can see that this path highlighted by this red line, that is the path that we are interested in analyzing. For example, we want to estimate the delay of this path. Now you can see that on this path you have two branches, one branch appearing at this node, another branch appearing at this node. Okay, so branching effort associated with a branching node is given by the ratio of C on path plus C off path divided by C on path. So what is C on path? C on path means the capacitance of the gate falling on the path. For example, this NAND gate for this node, this NAND gate is on the path. Therefore, the input capacitance of this NAND gate represents the on path capacitance. This NOR gate is not on the path. Therefore, the input capacitance of this NOR gate actually is C off path, and divided by the input capacitance of again this NAND gate on path. So branching effort of this node is given by, of any node that where branching occurs, is given by this ratio, right? Now for a given path, we have a parameter which is referred to as path branching effort. So path branching effort, which is represented by capital B, is actually given by the product of the individual branching efforts. That is, you have a branching effort associated with this node, you have a branching effort associated with this node. So for this path branching effort will be given by the product of the branching effort at this node and the branching effort at this node. And therefore, the total path effort is given by the product of the path logical effort, path branching effort, and path electrical effort. So these are the parameters of method of logical effort for multi-stage logic network. Now let us see how we can estimate delay of a multi-stage logic network. So to estimate delay of a multi-stage logic network, we define a parameter path effort delay. For a gate, we are having a stage delay or effort delay. For a multi-stage logic network, we have path effort delay that is represented by V with subscript F, and it is given by the summation of the stage delay of logic gates falling on that logic path in a multi-stage logic network. Now we know that the stage effort or effort delay of the logic gates falling on that path is given by the product of the logical effort and the electrical effort. So it will be given by this, and path parasitic delay is given by the summation of the parasitic delay of logic gates falling on that path. So you have these logic gates falling on a path, for example. So the sum of the parasitic delay of those logic gates, that gives the path parasitic delay, and therefore the total path delay can be written as the path as the sum of the path effort delay and the path parasitic delay. The sum of the path effort delay and path parasitic delay is actually gives us the total path delay. So this is the method how we can actually estimate the delay of a multi-stage logic network using the method of logical effort. Now we have to minimize the delay of a given logic network. So we have learned, till now we have learned to estimate the delay. Estimate the delay. We can estimate the delay of a single logic gate driving a given load, or we can estimate the delay of a given multi-stage logic path driving a given load. Now the next goal is to minimize the logic delay or to minimize the path delay. So to see how we can minimize the path delay, we are considering a two-stage network here, which is driving a capacitance C3, for example, and C1 and C2, they are the input capacitance of this gate 1, and C2 is the input capacitance of gate 2. And we are taking it as a general gate, any gate could be there. Therefore, the logical effort of gate 1 is represented as G1 and logical effort of gate 2 is represented as G2. And parasitic delay of gate 1 is given by P1 and parasitic delay of gate 2 is given by P2. Now, we have just learned that the delay of this path can be written as the delay of this gate plus delay of this gate. So, this represents the delay of gate 1. This represents the delay of gate 2. Okay. Now, and together they represent the delay of this path. Now, in this given path, H1 is the electrical effort of first gate. So we can write the load capacitance for first gate to the input capacitance of first gate. Now the load capacitance to first gate is nothing but the input capacitance of gate 2. Therefore, we can write H1 as C2 upon C1. Similarly, electrical effort for gate 2 can be written as the load capacitance, which is C3, divided by the input capacitance of gate 2, that is C2. So we can express or write electrical effort for gate 2 as C3 upon C2. And the product of H1, H2, that is given by, that will actually be C3 upon C1, because when you multiply the two, C2 gets cancelled. And if you recall the path electrical effort, so path electrical effort is given by the load capacitance divided by the input capacitance. So that is what you have got here. So this product of H1, H2 is nothing but the path electrical effort. Right? So therefore, we can actually rewrite this delay expression by replacing H2 by h upon h1. So we have actually replaced this h2 by h upon h1. So now we have this expression. Now we know we have an equation. We have to find the minima of this equation. Okay. And in this equation, G1, G2, that is fixed because the gate is fixed. P1, P2, that is parasitic delay, that is also fixed. The only thing that changes is H1 in this equation. So when you differentiate it with respect to H1, so you get G1 and this is 0 minus G2 H upon H1 square. So equating it actually gives the value of H1 that minimizes this function. Okay. So from here, from finding the minima of this, we get the condition, we could get this condition. So when you equate it with this, we get this condition that for minimum delay, G1H1 shall be equal to G2H2. Had there been 3 stages, the condition will remain same. That is G1H1 shall be equal to G2H2 shall be equal to G3H3 and so on. So what we conclude from here that path delay is minimized. Path delay is minimized when each stage bears same effort delay with F. So G1H1 is the effort delay of gate 1 F1. G2H2 is actually the effort delay of second stage gate F2. So what we conclude from here that the delay of a multi-stage logic network is minimized when each gate bears same stage effort. That is the conclusion from this analysis. And this conclusion will actually be used for transistor sizing and minimizing the delay of a given logic network. Now, calculating the minimum path delay. Till now, we have calculated path delay. Okay. Now we have to calculate minimum path delay. We are interested in estimating the minimum possible delay for a given path. Okay, you may be given 2 stage, 3 stage, 4 stage, n stage network. So before you can actually go on doing the sizing of the transistors and analyzing, you can actually estimate the minimum possible delay for a given logic network without even sizing the transistors. And how you can do that? So you can actually calculate the branching effort, electrical effort, logical effort, that all you can calculate, okay, for a given network. And from that, you can actually estimate path effort, which is given by the product of the path logical effort, path branching effort, and path electrical effort. Now, we have just seen that for minimum delay, every stage shall bear same stage effort. So, what does it mean? That G1H1 shall be equal to G2H2 shall be equal to GNHN. So, if we put this condition, this requirement for minimum delay here, if we put it here, so what will happen actually, you will have GIHI raised to the power n is equal to F, this path effort. And therefore, GIHI can be written as the total path effort raised to the power 1 upon n, where n is the number of stages in the given network. Okay. So, this thing actually is given by the stage effort for minimum delay, and therefore this thing is represented by F with a hat sign. So F with this hat sign actually represents the stage effort for minimum delay, and stage effort for a minimum delay in a given logic network is given by the path effort raised to the power 1 upon n, where n is the number of stages in the given network. Now, once that we have got this expression for the stage effort for minimum delay, we can rewrite the delay expression. So now there is a hat over this D. So what it means that it's the minimum delay, expression for minimum delay. So expression for minimum delay for an n-stage logic network is actually given by the n, which is number of stage in the given logic network, multiplied by the stage effort for a minimum delay, that is nothing but the path effort raised to the power 1 upon n plus the total plus path parasitic delay. So this is the delay expression, minimum delay possible for a given n-stage logic network. Now comes the gate sizing. So once you have estimated the minimum delay for a given logic network, you can see whether your delay constraint is satisfied with the logic network or not. If it is not satisfied, maybe you need to restructure the logic network to satisfy the delay constraint. Once you have got the logic network such that it satisfies the delay constraint, you can embark on gate sizing. So for gate sizing, you can actually start from the output side. So what the minimum delay requirement requires that every stage shall have equal stage effort, and stage effort is given by GH. So when you start from the output side, so for the last gate in the given logic network, you can write H as C out upon C in, where C out is the output capacitance connected at the output of the logic path, and C in is the input capacitance of the gate, last gate of the logic path. And logical, this G represents the logical effort of the logic gate. And from here, actually, we can write the input capacitance of that logic gate that is equal to the logical effort of that logic gate, which only depends on the type of the gate, okay, multiplied by the output capacitance divided by the optimum stage effort that you have estimated by f raised to the power 1 upon n. You have already estimated this. Okay. So working backward, that is, you will start from output side and you will go on from output side to the first gate in the logic network. For example, let us see the logic. So for example, if this is the logic path that you are analyzing, so for transistor sizing, you will start from this gate. Okay, backward, you will start from this gate. So once you have fixed the size of this gate, now you know the input capacitance. Now once you know the input capacitance of this gate, which is acting as the load capacitance for this gate, you can size this transistors of this gate, and so on. You can go backward and you can size the transistors. Always every gate satisfying this requirement. So you have to actually you have to actually ensure that all the gates falling on the logic path actually satisfies this requirement. So this is example problem. Let's leave it. Let us come to the number of stages for minimum delay. So now we are interested in path sizing. So till now what we have seen the use of method of logical effort for estimating delay, then using the method of logical effort for sizing the transistors of logic gates in a given logic network for minimizing the delay. Now the third thing that we need to discuss is path sizing. So let us first of all, to make you appreciate that path sizing can actually minimize the delay, let us consider this fourth situation where the driver, this inverter is the driver and this 64 is the load. So this one here actually represents that you have a unit capacitance or input capacitance of this inverter, and this 64 means you have this load capacitance is 64 times the input capacitance of this inverter. So here you have only one inverter driving this load. Here you are having two inverters driving this load. Here you are having three inverters driving this load. Here you are having four inverters driving this load. And in all these three cases, these numbers actually, they indicate a scale factor for those inverters. Means when you are using two stages, the transistors have been sized up. Okay. So this inverter is actually 8 times the size of this inverter. Here this inverter is actually 4 times the size of this inverter. This inverter is actually 4 times the size of this inverter. And similarly here you have a different scale factor. Now if we analyze using the method of logical effort, we can actually analyze these 4 networks given. So number of stages in this network is 1, in this network is 2, in this network is 3, in this network is 4. And the effort, path effort, so this actually, the, the path effort for this network, you can see that is 64, this is 8, this is 4, this is 2.8, right? Now, if you use the method of logical effort, this delay expression, if you use this delay expression, you can actually calculate the delay for all these 4 networks, and you can see that same load is being driven by that same driver inverter, but we have different number of stages in these paths, and therefore you are getting different delay values. So what you see that this is the fastest, you are getting a delay of 15, and this 15 is unitless quantity because we have not multiplied by tau here. So it's a unitless quantity. So what we conclude from here that adding at times adding a stage to a given logic network actually reduces delay. Okay, so this example was just to make you appreciate that at times adding a stage. So it was a single stage network, and here we are adding 2 stages, so it becomes 3 stage network, and it has actually reduced the delay. So it is beneficial to add stages in a given logic path. So let us see how we can calculate best number of stages for a given network. So you are given with a logic path. Okay. So how we can calculate the best number of stages for that given logic path. So let us consider that you have a logic network, given logic network, which has n1 stages. Okay, this is the logic network given, which has got n1 stages. Now you are adding inverters between the output load and the output of this logic network. You are actually adding stages. And for adding stages, you will actually be adding inverters. That is the case. Okay. So what we are assuming that after adding stages, this becomes n stage network. This becomes n stage network. The given network was n1 stage, and you have added n minus n1 extra inverters between the load and the logic network, so that this network now becomes n stage network, right? So if we write the delay of this n stage network, we can write the delay of this n stage network as n times the total path effort raised to the power 1 upon n, that is the best stage effort, plus the delay of the parasitic delay of the path parasitic delay of the given logic network. So this actually represents the path parasitic delay of the given logic network, and this n minus n1 p inverter actually represents the parasitic delay introduced by these inverters. And one thing you shall be sure that you see this F, capital F, it will not change by adding the inverter, because see, when you are adding inverters here, the logical effort of inverters are 1. There is no branching effort. Okay. And electrical effort will, of course, path electrical effort will also not change, because path electrical effort is given by the ratio of this capacitance to the ratio of input capacitance. So adding inverter into this given logic network does not change this thing. This thing does not change, which is given by GBH. GBH. This F is given by GBH of this given logic network. So that does not change by adding this inverter, because the logical effort of inverters is 1. However, the total number of stage has changed. Earlier it was N1 stage. Now you have made it N stage. And that is why this product N and 1 upon N comes here. Now again, we will follow the same procedure that we have to actually find the best number of stages. That is, we have to find the value of N that actually minimizes the delay. So what we will do, we will differentiate this delay expression with respect to N. And when we differentiate this delay expression with respect to N, so we get this thing. Okay, and this is not a simple equation actually. So it is very difficult to solve this equation analytically. You will have to solve it numerically. You can feed even this equation into the Excel chart and you can solve this. Now at this stage, to simplify this expression, we are defining a parameter base stage effort, rho. So rho, base stage effort rho is given by f raised to the power 1 upon n. Right? So this equation can actually be written as P inverter, I am writing it here, and then this thing can be written as rho multiplied 1 minus ln rho. Right? So this thing now can be written as this by replacing f raised to the power 1 upon n by rho, which is the best stage effort. Now when we solve this equation numerically, by putting P inverter is equal to 1 in method of logical effort, P inverter is assigned a value 1. This is also an approximation. Actually, the method of logical effort itself is full of approximations, but it's very simple method. That is why it is also referred to as back of the envelope calculation. So by replacing P inverter by 1 and then numerically solving this, you get the value of rho that is equal to 3.59. Now, one thing at this point I shall tell you that it is not very strict that you shall take the value of 3.59 only. Even if you take the value of 3 rho in the range of say 3 to 5, for example, you can take, and there will not be much variation in the delay. Okay. So for the simplicity of the calculation, the rho is actually for calculations. To keep the calculation simple, rho will often be assigned a value of 4. So when you assign a value of 4 to this rho, you can actually write the expression for n as n is equal to log of f base 4. Okay, and to be more accurate, you can even put 3.5 here, no issue. Okay, so now using this expression actually, but this is the practice that we use 4. The value of rho, that is best stage effort, we take the value of best stage effort as 4. Because even when you vary it between 3 to 5, it will not affect the delay much. So from here you can see we have got the expression of n. Okay, so if the logic network is given for which you know the f. Okay, you know the f. So knowing the f, you can actually calculate the number of stages that shall be there in this logic network for minimum delay. So this is how we calculate best number of stages in a given logic network. So we have learned to estimate the delay of a given logic network. We have learned to size the transistors of gates in a given logic network for minimum delay, and we just learned how to how to find the number of stages for a given logic network for minimum delay. So this finding the number of stages of a logic network for minimum delay is also referred to as path sizing. So this is referred to as path sizing, means you are sizing the path, you are adjusting the number of stages in the given path to minimize the delay. Okay, so these are exercise problems. So I think this is the last slide that I would like to do today, because we have already finished the time limit. So that stick diagram and layout thing we will do in lab session. So here we can review the various parameters and their expressions in the method of logical effort. So for a single gate, the number of stage of course will be 1, and for a n-stage logic network, for a given path, the number of stages will be n. For a single gate, the small g is used to represent the logical effort of that gate, and for a path, we actually calculate the path logical effort, which is given by the product of the logical effort of individual gates falling on that path. For a logic gate, electrical effort is calculated as the ratio of the C out of the CL upon C in, and for a path, it is path electrical effort, which is given by the C out path upon C in path. Similarly, branching effort for a logic gate, you can have a branching effort like this, and for a path, you will have path branching effort. And effort delay for a logic gate, you have effort delay. For a path, you have path effort delay given by the product of path logical effort, path branching effort, path branching. And then you have effort delay for a single stage logic gate and effort delay for a given path, that is sum of the stage effort or effort delay of individual gates. And then parasitic delay for a logic gate and path parasitic delay of a path. And we have finally the delay expressions. So that's it for today. So I am done. Now the session is open for questions. If you have any query, you can ask.
Naushad sir,
Yes.
thank you very much. And I think madam or somebody, let me see. Somebody has asked from where you got those equations, which book you are referring for logical effort equation.
Pardon? Can you please repeat? Which equations?
Logical effort equations, all related equations, no?
Delay equation, sir. Sorry, I have unmuted myself. It is delay equation, sir.
No, I'm not. You are asking about the delay equations?
Sir, book.
Equations you are asking about?
Sir, okay, can you hear me clearly?
Yes.
Yes.
Only the book?
Yes.
So I have referred two books. One book is Digital Integrated Circuit by David Hodges. Digital Integrated Circuit by David Hodges.
Sir, can you write in the chat box?
Yeah, okay, I will write surely. Yes, I will write. Chat box, yeah, yes.
Okay, in meantime, anybody has a question, anything else?
Sir, hello, sir.
Okay, just wait.
I have posted it in the chat box. Is it visible?
Yeah, yes, sir.
I have posted the name of the book. Is it visible there, Rathod sir?
Just a minute, sir. No, sir, I think, sir, you have not selected everyone from there.
Okay, there.
I'll come out of your presentation mode so that you can easily write. Okay.
Right,
That's the
okay.
issue. That's the issue. Here. So now you type.
So, okay, now I will everyone.
Hello, sir.
Yeah, please, just a minute, just a minute.
It's okay, sir.
I'm not able to write a chat. Why?
Sir, why you're not able to?
I'm not able to. Yeah, I've got it. Yeah, I'm posting it. And I have posted now.
Yeah, we got. The other book you said, sir? David Douglas and
Another book is here. Another book is yes. Just it's a method of designing high speed CMOS logic. Another book is
Sutherland.
Sutherland.
Yeah, Sutherland. Okay. Someone was asking the question.
Yes.
Hello, sir. Hello, sir.
Please go ahead.
Hello.
Sir, for getting minimum path delay, we understood that the stage effort of all the stages must be equal. So, is it sufficient if we choose the value of n, that is addition of inverters, using the equation log f to the base 4?
I did not get the question. Rathod sir, can you please repeat the question?
No. Ma'am, please repeat. No, slowly. You speak slowly.
Okay, sir. In order to get the minimum path delay,
Yeah.
we need to have the stage efforts of all the stages equal.
Yes.
So, in order to get that, are we supposed to get the value of n that is equal to log f to the base 4? It is sufficient, sir?
Okay. Yeah, I got your question. So, Rathod sir,
Yes.
can you share my slide?
Okay.
Enable me to share my slide. Yeah. Thank you. So, right, madam. We are here, Ram. So, what we have three things. We did in three things in the method of logical effort. The first thing is to just estimate the delay of a given logic network. That's it.
Right, sir.
So we can estimate the delay of logic network by following the method of logical effort.
Okay.
The second thing we did to size the gates of the logic network for minimum delay.
Right, sir.
So we may be given a logic network and we are not allowed to change the number of stages.
Okay.
We are not allowed to change the number of stages. So when we are not allowed to change the number of stages, how can we minimize the delay of logic path? So that we can do by sizing the transistors again. Now
Okay. Okay.
another case, third case could be that we are allowed to change the number of stages. Right? So whenever we are allowed to change the number of stages, so it is actually known, it is concluded that if you are allowed to change the number of stages, then you shall always make the number of stage, you shall always actually make the stage effort equal to 4. So
Okay.
all the stages shall have a stage effort of 4. And with that stage effort of 4, you can get the number of stage n that will actually give you minimum delay.
Okay, sir. Okay.
So if you are not allowed to change the number of stages, it will be the stage effort that you get for minimum delay can be more than 4 something, anything, can be anything here. You can see,
Okay.
if you are not allowed to change the number of stages, if n is fixed, this stage effort for minimum delay, it could be 3, it could be 5, it could be 10. If you are not allowed to change the number of stages. But if you are allowed to change the number of stages, the most stage effort will always be 4, or you can have it in the range of 3 to 5.
Okay.
Did I answer your question?
Yes, sir. Yes, sir. Definitely.
Sir, Surendra Rathod, may I come in?
Yeah, ma'am. It's coming. It's coming.
Sir, I feel that the number of stages depend upon the load you have to drive at the output and the capacitance of the first transistor, that is the input transistor. So CL by CG is F. And then F, we decide, that is, if we consider 4 is the optimum size of the each stage, then there is a sort of increasing size of the inverter, next inverter, so that finally the total electrical effort is satisfied, which is F raised to 1 by N. So N should be chosen in such a way. N basically is not the number of stages. I think N is the number of stages. But what we have to do is that we have to find out, depending upon F, what that N should be, so that the delay is minimum. That is what I feel.
Okay, ma'am.
I think nth root of F. Nth root of F. Yeah, bolo, sir.
Ma'am, what I'm saying, that you may have two situations. In one situation, the multi-stage logic path is given and you are not allowed to change the number of stages. So number of stages is fixed. Load is fixed, number of stages is fixed, and you have to size the transistors of the logic gates to minimize the delay. Okay?
Yeah, but
in that
the
case,
behavior, yeah.
In that
Yeah,
case,
sir.
In that case, the best stage effort will be given by F raised to the power 1 upon N. Fine.
Yeah. Yeah.
And this N is actually fixed. You are not allowed to change N. So using this number of stages in the given logic network, you can find the value of stage effort for minimum delay. Now this stage effort for minimum delay can be any number because you are not allowed to change N.
But I think, isn't it a wrong design parameter? Because giving N in the hands of a designer will be better, because the behavior of normalized delay or the delay versus F shows something that after some F, the delay will not be minimized.
Yes,
It comes to
I'm coming to that point only. So we considered a given N stage network, and where we can actually calculate the minimum possible delay for that N stage network, and we can actually calculate the stage effort for minimum delay in the given network. Now यहाँ से भी हमको hint मिल जाएगा. We can get a hint from here that shall we add some stages or not. For example, if we are getting this stage effort 11, so we know that for optimum path, the stage effort, best stage effort shall be nearly 4. So from here also we get an idea that okay, the given number of stages are not optimal. But consider a situation that you are not allowed to change the number of stages. So what best you can do for minimizing delay is to size the transistors. Okay. And that sizing of transistors can be done to satisfy this requirement that every stage bears this stage effort. Am I okay, ma'am?
Yeah, it is okay, but still I am not.
Then next case is that okay, you are allowed to even change the number of stages in the given logic path. So if you have that flexibility also, in that case, what you will do? You will assign a stage effort of 4 to all the stages. That is a magic number actually. This 4 is a magic number. Okay.
Yeah.
So you will assign a stage effort of 4 to all the stages.
Okay.
And then using this F, you can calculate how many stages do you need in that logic path.
Yeah.
So if you have, say, suppose you got 10 stages from this calculation. Now the given logic network is having, say, 6 stages. So you will have to add 4 inverters here so as to make the number of stage 10. And that will actually give you the minimum delay. I hope I answer your question.
Yeah. Okay. Okay. But the size of the next inverter will go on increasing, like it is a horn.
Yeah, that goes on increasing.
Yeah.
That of course goes on increasing.
Okay, sir. Thank you.
Thank you, ma'am. Thank you very much. Yeah.
Sir,
Yeah. Please go ahead, sir.
Current ongoing technology is 7 nanometer. Sir, current ongoing technology node is 7 nanometer now. So in that
7
aspect,
nanometer is in commercial production.
what is the approximate thickness of the oxide layer, sir?
See, oxide layer has not gone below, say, 1 nanometer. If we talk about silicon dioxide, although in the current technology, silicon dioxide is not being used as a gate oxide, it is mostly hafnium dioxide, right?
Sir, if we are going to hafnium oxide, electric constant of hafnium oxide more, na, sir, compared to silicon dioxide?
Of course, it is nearly 20,
5, approximately 25.
yeah, 20, 25, yeah.
Yeah, now it is going to increasing the gate capacitance, na, sir?
Yeah, gate capacity.
Of course.
Okay.
Of course.
Of course.
So now it is going to affect the delay, na, sir?
See, when we talk about gate capacitance,
Okay.
the gate capacitance between the gate and the channel, okay, that is
Okay.
actually desired capacitance. So if you are saying that gate capacitance is increasing, to recall the current equation. Current equation is half mu Cox W upon L VGS minus VTH whole square.
Yeah.
So Cox, if you are increasing Cox, actually it is helping you to increase the current.
Okay. Okay, sir. Okay. Thank you. Thank you, sir. Thank you very much.
Yeah, but it was a nice question actually. Yeah. Thank you. Anybody else has any question?
Uh, can I again pose some question or just the discussion?
Yeah, ma'am. Please, you are most welcome.
Sir, generally the boundary parameters will be COX, that is oxide capacitance per unit area, and overlap capacitance will be capacitance per unit length. And hence, I think when you consider the junction capacitance as such, is bottom junction capacitance is always considered, that is you consider L into W as the area because COX is per unit area, while the overlap capacitance, I think when the transistor is in the linear or the saturation mode, the side which is adjacent to the channel doesn't come into picture, but the other length and two lengths of the source or drain that come into picture. So 2LS plus W into overlap capacitance, which is per unit length. That will give you the total junction capacitance. That's what my thing is, because boundary parameters are generally for the junction, bottom junction capacitance is per unit area, whereas for the overlap is per unit length. So the terms should be, the other term should be in terms of the area when we multiply, and for overlap it is in terms of the length only. So I think perhaps this book which you are referring gives that way, but the technology parameters, the boundary parameters, if you see, they generally are like this. It becomes easier for understanding also. Any comment on this, sir?
It's okay, ma'am. Thank you, ma'am. Thank you very much. Ma'am, I have one doubt, ma'am. That is, so in 7 nanometer technology, how much approximate width the thickness of the HF, even HF02 also? What is the approximate thickness they are using?
Basically, I think the other question also somebody had asked, if you increase the dielectric, basically the increase in the dielectric to reduce the oxide thickness, because with SiO2, you are going to the one atomic length only as the thickness of the oxide. So that gives the limitation. So when you are going down in scale, you have to go to a dielectric of higher dielectric constant so that the thickness can be reduced. And that is why I think we are working on high dielectric materials as the research area for low. That is what my impression is.
So, okay, that means up to atomic level thickness only they are using.
Atomic level of that material,
Okay.
that is the limitation. What you are
Okay.
HF you are talking about. Yeah, that is the limitation. You cannot go below that. But if you have a higher dielectric, you can reduce it than that for SiO2. SiO2, you have already reached the limit.
Okay.
Yeah,
Thank you,
ma'am.
ma'am. Thank you very much.
Yeah, ma'am. You are right. This is what is the answer. C0x per unit area capacitance. So epsilon by T.
Yox like yox.
Either reduce your oxide thickness or you can increase the permittivity. So reaching the limits of the atomic layer. So it is impossible, no, below going, because it's level, below 1 nanometer. It's not possible at all, and therefore only option left is increasing the oxide permittivity. That's the only option. So ma'am's answer was perfectly correct, I believe. So, anybody else would like to have anything to be discussed?
Sir, for the participants, I would recommend a book by Ravi on D2
Ravi.
integrated. Yeah.
Yeah.
It's Jan Rebe and Chandrakasan and Nikolik.
Yes,
It
yes.
basically deals with 0.25 micron technology. The other books, I think, West and all that deal with micron technology. So to have the latest knowledge, I think participants also can refer to Ravi's book. I think that is my recommendation.
Yeah.
Ma'am, I would like to add something to your recommendation. Of course, Rabbi is a very good book and very standard book. Some positive points with the book that I have recommended by David Hodges is that this book actually includes some example SPICE codes for extracting parasitic capacitances, gate capacitances, all those capacitances using SPICE simulations. So that will actually be very useful for the faculty or the students beginning with these kind of simulations and want to extract those parameters.
In the learning phase, it's okay. For the basic, any book can be referred, no doubt. But to get an idea
Rabbi's book is a little advanced book. So before Rabbi, this Hodges book may be read. And if somebody can cope up with the advancement of that advanced nature of that Rabbi's book, it's really good. It's really good.
Okay, sir. Thank you, sir. Thank you.
Ma'am, can you please give the book name in chat box, please?
Yeah, I will give.
It helps a lot. Thank you, ma'am. Thank you very much.
Sir, John Rabe, it's a popular one of John Rabe.
Yes, it is very popular.
Sir, due to network problem, it is not listening, not listening properly, sir. Sir, thank you, sir.
Maybe I should be right here.
I'll write.
Yeah, ma'am. Sir, shall I take out the PPT? Your this thing presentation, Naushad sir.
Yeah, I can mail you, no issue. Or
no.
You can take...
No. I'm saying now through presentation mode.
Is what shall I do? What do you need?
No. Wait. If nobody has a question, then we can let me see. Okay. So good. We had a very. And we are actually fortunate that ma'am is with us. Probably Naushad sir doesn't know about Shaila ma'am, so I just would like to brief. Shaila ma'am is a kind of a mentor for us, and she has just retired. Lots, one of our speakers also, and she is so interested after returning also. Ma'am, you are like I don't know, no words for me to speak, and you are still so enthusiastic and so passionate to learn about VLSI technology. It's really, I mean, grateful. And you are a participant, so I'm sure we will have a very good discussions going throughout the sessions. Thank you very much for joining us, ma'am.
Basically, such things keep me young. I don't feel that.
Okay, very nice, ma'am. After working for 30-40 years in VLSI domain, you still see you are talking about gate oxide thickness permittivity, where people simply forget about it. It's really simply a motivation for us. And great, ma'am. So, participants, just few instructions because we had a difficult situation. Really, it was a very difficult situation for us today to cope up with all kinds of problems, network connectivity to power failure, everything because of power failure primarily in Mumbai. And there was in fact locals also failed. So water supply, local, everything failed just because of power. So important power aspect is in our life. So what we have to do is now, because this was a theory session, it was planned in the morning today, and actually at 5 to 7 today, it was supposed to be the practical session, hands-on session on LT-SPICE, which Naushad sir, he himself was about to take. But then today, because of this thing, we were not able to take it. So I want your opinion that when we should have this 2 hours of session, either tomorrow or day after tomorrow. But then one day you will have to compromise because there is no other way for this. Correct. So I have simply opened a poll. As you can see the poll, it's open in your chat box, and there are 4 options. I want to see the majority option what you was talking about. It is actually mentioned tomorrow in the question because I planned it tomorrow, but Naushad sir's preference is Wednesday. So assuming Wednesday, can you put option 5 to 7? You don't want it at all. Yeah, maybe any day is okay. Shifting on any session is okay, or you don't have any opinion. So we will immediately come to know what is your opinion. Put your poll. It's open in the chat box. You can see your poll. I'm starting getting answers. Take kind of a demonstration, and then actually Naushad sir can speak if he wants to speak. How we will proceed with those 2 sessions. They will not be theory. They will be like a demonstrations on LT-SPICE and layout versus simulation. We are not going to disturb other regular sessions, right? Whatever it is planned, you have to compromise on these 2 hours. Preferably evening, because tomorrow and
Sir, there is question regarding downloading those tools. Hello?
you can ask Naushad sir. Naushad sir, are you there?
Yes.
Yes, sir,
I'm-
ma'am. SPICE electric. So seems to discuss something. Ma'am, please ask.
Yeah, I think the procedure has been given by S.P.I.T coordinator, and as per that procedure, I downloaded both the files. One was Java and the other one was electric binary, something 9.07. But that binary electric simulation file is having which extension? Because when it says open the file with what, I do not get the extension of that, so I was not able to open and go with the procedure. So can you highlight on this, sir?
Sure, ma'am, sure. Actually, it shall not ask for that. So, see, my screen is visible. Rathod sir?
No, sir. Just a minute. I will close the poll so that we can see the. Just a minute, sir. I'll
लेकिन जो मेंटर थी गए रिटायर होके भी 4-5 साल का उसको स्टार्टिंग में इस साल में बीएनएसआई में फरी गए इतना है उसको
Okay. So our poll results are with us. We can discuss that. Results are what? So finally, what is the poll result? 24 have responded. I don't know why people are not responding, even if they are present.
The statistics.
Statistics, yes. So, Naushad sir, I will share the presentation screen.
Shall I share?
Yes, sir. Yes, please go ahead.
Okay. So the document that I have shared,
Yeah.
so this is that document.
Yes.
So for which the URL for the download of electric is given.
Yeah.
So actually, I will do it before you.
Yeah.
I copy the URL and then I go to. So is my tab visible to you? You see the web page that I opened?
Yes.
Just a
Yeah. From this web page, you have.
No web page.
Sir, no web page, sir.
Okay, let me see what.
Share again. Stop this one. Share again.
Okay. So I shall stop this and then I shall share the web page. Yeah, this web page from where you can download React. So we
Yes.
have actually two options here, electric source and electric binary.
Yeah.
So we shall download electric binary,
Okay.
right? And once we have downloaded electric binary, next step was to install the runtime Java environment.
Yeah.
So if you have downloaded the binary release of the electric and installed the Java environment,
Okay.
runtime Java environment, you shall be actually able to invoke. I will show you the folder. You shall be able to invoke of
Sir, what happened?
yeah, I will share the screen.
Okay.
So is it now is it visible now? So once you have downloaded, this is, for example, this is the older version of Electric 9.06, and I have installed the Java runtime environment. Okay.
Okay.
So now when I double click on this, it will actually invoke Electric. So this is what opens up. So till this point, we don't need that LT Spice. LT Spice we need only for Spice simulations.
Okay.
So
Okay.
this electric actually pops up. So were you seeing something else in the folder while poking this electric binary?
Now, electric binary was open only after Java was installed.
Yes, Java runtime environment that is required.
Because it is not given like that.
No, I have given it in the Word file that I shared.
Yeah. Yeah, after installation. Yeah.
No, actually, you need not to install electric. Electric is actually executable binary file. You need to just download it.
Okay. Okay.
You need not to install that. And once you have downloaded, if the Java runtime environment is not installed on your system, so this icon will not be visible like this. It will be something
Yeah,
else.
icon. Yeah, for me, icon was not visible.
Unrecognized kind of
Yeah,
file.
something. Yeah, correct. Something like that.
So if you are seeing that, it means that Java runtime environment is not properly installed. Please ensure that the runtime Java environment is properly installed.
So that needs to be installed as per the configuration of your laptop, which is x86.
Actually, when you will go to the given URL, it will ask the system configuration, and then it will.
No, it doesn't ask the system configuration. It has given number of options like Solaris and 32-bit and all that. So correspondingly, I chose the configuration of my PC, which is 64-bit.
Yeah, that 34-bit, 64-bit information it may ask. And okay, let me open that URL also. So that is this URL.
Yes.
So from here we can actually install. We have this Java runtime environment for Linux, and we have Windows.
Yes.
So from here we can actually install Windows. To be specific, what I have installed. So do you see my folder? This folder. So means from here actually we can install the Java runtime environment as per the operating system and as per the system.
Yeah, I selected Windows x64.
So then what happened, ma'am? Didn't it install?
No, I got the download of that, but then I think I need to install it. I went for electric binary just after downloading that file. That perhaps was the problem. I'll look into that again.
If you are doing it right now, you can also share your screen, and then I can.
I'll do it later on, sir. And if problem is there again, I can ask you.
Madam, Shaila madam.
Yes.
What we will do is we will close this meeting. If you have time now, then we will wait now in the meeting, and you can share your screen and we can sort out the issue if you want.
Okay. Okay.
If you have the time, we will
Sir,
sort it out.
why I have a doubt is that mine is Windows, and when I try to do something with Linux, something happens and it gets corrupted. The same thing happened some 4 days back. So I was not ready to really proceed with that. But I think we can try it once again.
Okay, ma'am. We will see. So
Because
for other participants, yeah. So we will simply close the meeting for other participants. We can tell them. So thank you, Nishad sir. Thank you very much. And we will get back to you. Your opinion poll, which I have taken, is very fragmented opinion, I can say. Because, I don't
you
know.
dis-
People are saying Wednesday or Saturday. People are saying. So we will decide on that. We will take a call with Navshafa and we will let you know accordingly. Okay. So thank you very much. Join tomorrow morning 10 a.m. And yes, please, I will open the Moodle quiz form. Few questions will be there. Every time we will have 10 to 15 questions. You go on and I'll ensure that questions are okay. You please fill up that list so that we will have a continuous assessment and we will not be burdened with or you will not be burdened with the last examination as such. Okay. So, and it will be open from morning 8 a.m. to 10 a.m. In between, you can log in any point of time, and probably we will have, let us say, 15 or 20 or 30 minutes maximum. You will need to appear for that. Okay. So,
Sir,
thank you very much. Yes, ma'am.
kindly post that Moodle procedure on mail because the chat box will get closed.
Me ठेवली madam. I have posted.
Okay.
Okay, I already made. Okay. ठीक है. Thank you very much. So thanks all. Others can leave. Those who want to leave, and then ma'am and we can have a discussion on the this thing if he is having the issue with the installation.